Hey guys, last week we started a new mini-series that begins with introducing the imaginary number I and other roots of unity. We defined the complex numbers and their addition and multiplication. Also, make sure you are comfortable with all of the exercises and results that we got in that video. We will use the same format as last week for small exercises. Namely, we want to give you the chance to solve them on your own, and we again uploaded all the solutions already as YouTube shorts. Today we will investigate our last result from the previous video that tells us that we can factor any polynomial into complex linear factors. We want to calculate the exact factorization for a type of polynomial that is not generally factorizable under the real numbers. Namely, we are going to be concerned with the polynomials x to the power of n minus 1. We are familiar with factorizations for some small n. For instance, x minus 1 is just a linear factor on its own. Moreover, x squared minus 1 equals x minus 1 times x plus 1. From last week, we can now add to this list that x to the power of 4 minus 1 equals x minus 1 times x plus 1 times x squared plus 1, which we now know to be equal to x minus I times x plus I. To better understand these polynomials, we want to get a visual representation for this. So we go back to the beginning where we defined the complex numbers. Since we noted that I is not a real number, we can associate each complex number a plus bi with a pair of two real numbers a comma b. This suggests a mapping from the complex numbers to the plane r squared, which we then call the complex plane, where we map the complex number a plus bi to the point a comma b. Let me draw in this plane where I'm going to mark the roots of these polynomials. This is the complex plane, and I quickly want to note that by the way we have defined it, if we consider some complex number, for example 1 plus I, and its coordinates in this plane, then its x value is equal to the real part of that number and the y value its imaginary part. And here those two functions are defined in the intuitive way, namely the real part of a plus bi should be a and its imaginary part is b. We see that the four roots of x to the power 4 minus 1 lie on the unit circle, which is the circle around the origin with radius 1, and are evenly spaced on it. This is the reason why I decided to draw this picture for you, because I want to give motivation for how we can find a general formula for the roots of x to the power of n minus 1. So we want to formalize this notion of a distance to the origin of a complex number and also get an understanding of how we can represent this even spacing. So we have to somehow deal with an angle that a complex number forms with respect to these x's. So let us define the absolute value of a complex number z to be the distance of the corresponding point in the complex plane to the origin, which is by the Pythagorean theorem equal to the square root of the square of the real part of z plus the imaginary part of z squared. We have seen in the calculations of two previous exercises that this is equal to the square root of z times z bar. This sets us up for exercise 3 of this mini-series. You are asked to confirm that the absolute value of z equals 0 if and only if z equals 0. Moreover, prove that absolute value z1, z2 equals absolute value z1 times absolute value z2. Can you find a new proof for exercise 1 using this result? It is left to deal with these angles around the unit circle. To do that, we define the argument of a complex number, take for example 1 plus I, to be the counterclockwise angle starting from the real axis towards the ray through the origin and the point associated with z in the interval from minus pi to pi. In other words, for a complex number z, we define its argument, arc z, to be the angle phi in the interval that is open at minus pi up to plus pi. Here, this choice of interval is really arbitrary because we can associate any angle phi with phi plus k times 2 pi. It really never does any difference, but here we choose that interval, and we choose phi in this interval unique with the property that we want z to be equal to cosine of phi plus I sine phi. If z lies on the unit circle, this is exactly working due to the definitions of cosine and sine, but we have to make up for the fact that z could possibly not lie on the unit circle, and therefore we have to divide by its absolute value here. Note that this doesn't work for z is equal to 0, and it really makes sense that we cannot define such an angle for z equal to 0, so here we write z not equal to 0, and for convenience define arc 0 to be equal to 0. The fact that such a unique phi exists is really clear if we take a look at a picture, but I invite you to verify this fact in the next exercise, which asks to prove that absolute value and argument determine a complex number uniquely. In other words, we are asked to prove that z1 equals z2 if and only if absolute value z1 equals absolute value z2 and their two arguments are also equal. And in exercise 5, we shall prove that the argument of z1, z2 is congruent to argument z1 plus argument z2 modulo 2 pi if z1 and z2 are non-zero. This means that there exists an integer k such that the difference of both sides is equal to k times 2 pi. From the definition of the argument, we see that the term cosine phi plus I sine phi is essential. Therefore, we also define the function e of phi to be equal to cosine phi plus I sine phi. Therefore, the absolute value of e of phi equals 1, and the argument of e of phi is congruent to phi modulo 2 pi. Using our previous result, that leads to the following representation for every complex number z. Namely, we can write z to be equal to the absolute value of z times e of the argument of z. We call this the polar representation of a complex number z, and it is, for instance, very useful if we want to multiply complex numbers. Because if we take a look at exercises 3 and exercise 5, then we see that a multiplication of two complex numbers corresponds to the fact that if we multiply z1 and z2, then we scale z1 by the absolute value of z2 and then rotate it in the complex plane around the angle argument z2 counterclockwise. So if we have the polar representations of z1 and z2, this easily gives us a way for multiplying them, namely the result is going to be absolute value z1 times absolute value z2 times e of argument z1 plus argument z2. This enables us to solve exercises 6 to 8. Firstly, we want to prove that e of phi to the power of k equals e of k times phi for any integer k. Moreover, we are asked to find the real numbers a and b such that a plus bi equals e of 2 pi over 8. Lastly, calculate c and d real numbers such that c plus di equals 1 plus I to the power of 100. All this enables us to complete our investigation of x to the power of n minus 1. Let us consider a complex number z such that z to the power of n minus 1 equals 0, or in other words, z to the power of n is equal to 1. Thus, 1 is equal to the absolute value of 1, or the absolute value of z to the power of n. We use our exercises to conclude that this is the absolute value of z to the power of n. And because this is a non-negative real number, that implies that the absolute value of z is equal to 1, so z must lie on the unit circle. Moreover, 0 is the argument of 1, or the argument of z to the power of n, which is by our exercises congruent to n times the argument of z. Therefore, the argument of z is equal to k times 2 pi over n for some k and z. In other words, we can conclude that z must be equal to e of k times 2 pi divided by n. Indeed, if we plug such a value into the polynomial x to the power of n minus 1, we get 0. Therefore, all of those values are roots of x to the n minus 1. Notice that substituting k plus n for k here doesn't change the value of z, because in our context the function e has a periodicity of 2 pi. So this gives us at most n distinct roots of the polynomial x to the power of n minus 1, namely for k is equal to 1 up to n. We can rewrite this as omega n to the power of k if we define omega n to be equal to e of 2 pi divided by n using exercise 6. The second to last exercise for you is to prove that these n values are indeed distinct. So prove that omega n squared, all the way up to omega n to the power of n are n distinct complex numbers. Using this fact, we can conclude that we have found n distinct roots of the polynomial x to the power of n minus 1, and since it is of degree n and has leading coefficient 1, all of that implies that x to the power of n minus 1 is equal to the product of k equals to 1 up to n of x minus omega n to the power of k. I hope that you enjoyed this new type of content. And here is a last exercise for you to warm up for the upcoming video. Prove that for any prime p and an integer I, the sum of k going from 1 to p of omega p to the power of k to the power of I is either p for p divides I and 0 otherwise. And as a small hint, use the factorization for x to the power of n minus 1 that we found before. Moreover, you can try to prove the more general result that this same statement holds if we replace p by any integer, positive integer n.